Well, good day, ladies and gentlemen. Here we are into another exciting excursion into algebraic knowledge. Our next section is linear inequalities. Now, a lot of you know that this prefix "n" means not. So we're talking about expressions of things that are not equal. And when we're talking about inequalities, we are specifically talking about this guy, which is greater than this guy, which is less than. And by the way, less than always points to the left. Good way to remember it. And of course, they're cousins. Greater than or equal to, and less than are equal to. So when we're talking inequalities, these are the symbols that we will encounter as we work our problems together. Just a quick comparing and contrast to solving linear equations versus linear inequalities. Let's look at a typical linear equation. This is one of your Hawk's problems. And let's compare that with a linear inequality. The good news about solving these guys is that basically, with one little exception that we'll get to in a minute, they solve the same way. I want to get y's on one side, numbers on the other. This side obviously has more y's, so I'm going to get rid of the y's on this side by subtracting 4y from both sides. Hey, this is my y side, so I don't need a number over here, so I'm going to add 18 to both sides. Divide by 2, y is 3. And I've just found my solution set. There it is. This is obviously a conditional equation. It's true under one condition, namely that y is 3. So my solution set is the set with one element in it, 3. Pretty easy. Like I said, this basically solves the same way as an equation. Let me just make a suggestion here. Most of you would naturally put the y's on the left because there are more y's on the left than on the right. My suggestion is this. Always put the y's on the left when you're solving an inequality, even if it makes a negative number of y's. Why? Because at the end, you will have an expression that begins with your variable. Y is less than something, greater than something. Y is. So y being the subject of your mathematical sentence. And it's easier to understand if I finish with a statement that says x is this or y is that. So it's a suggestion. Get your variables on the left side when you are solving an inequality. Hey, we were going to do that anyway, so it's not going to change a lot right now. Hey, I'm going to add 18 to both sides, just as before. Only difference is I have an inequality symbol instead of an equation. Divide both sides by 2. Y is less than 3. Now, my solution set. Hey, it's anything less than 3. Like 2, 2.7, 1.4, 0, negative 33, negative pi over 8, anything less than 3. Which brings me to a very important concept, and that is 3 ways to indicate infinite sets. This is an infinite set of values right here. Anything less than 3. I got a ton of stuff less than 3. There are an infinite number of values. So how can I write anything less than 3? Let me see if I can find a page that says that. Looks like I'm out of luck. I'm going to have to roll my own here. So I'm going to show you 3 ways to indicate anything less than 3. Three ways to indicate infinite sets. Hey, anything less than 3 is an infinite set. Let's use that for an example first. The first way to, and you're going to have to be familiar with each of these ways because in different sets of circumstance, each of them is used. The first is what is called a statement of inequality. It's going to use an inequality symbol. Statement of inequality. And it's going to use something called, maybe you've heard of this, set builder notation. It is the very formal notation. It's the very formal way of writing, indicating a set. It goes like this. The set of all x such that, this vertical line is read such that x is an element of the real numbers and x is less than 3. That's the set builder notation for this set. It's a description of my x's so that if I read and understand it, I can build a set out of this description. And it's read this, the set of all x such that x is an element of the real numbers, in other words, x is a real number, and x is less than 3. This once again is read such that. Once again, that is the very formal way to indicate anything less than 3, and we will not be using this often, but when you see it, recognize what it is. Secondly, more familiar is the number line. I can indicate a particular set by simply highlighting part of a number line. Typical number line, horizontal, point of reference, 0. Now on this number line, I want to indicate anything less than 3. So I'm thinking, since I'm talking about anything less than 3, marking 3 on my number line is going to be pretty important. So anything less than 3, is that to the right or to the left? Exactly, it's anything to the left of 3. So I'm going to indicate anything to the left of 3. All the way to the end, all the way to the left, as far as it'll go, infinitely in that direction. Now here's one thing that I haven't indicated is I have not indicated with my graph if 3 is a part of the graph or not. So here's a question. When I'm describing all numbers, anything less than 3, is 3 an element of this particular set? And you could ask it this way. Is 3 less than 3? Yeah, no. 3, of course, isn't less than 3. So I want to put some symbol that says, do not include the point 3. So you and I and Mr. Hawks are going to be using brackets and parentheses as our ending markers. Parentheses says do not include. Brackets say do include this point. So if I were to put a bracket here, that would tell me that I'm thinking 3 is a member of this set, but we know it's not. So I'm going to have to use parentheses. Now you're going to be doing this a lot on this section. You're going to be marking with a parentheses or a bracket the ending of your number line. So if you want to indicate that something is not part of the set, you're going to be putting parentheses. All right, that's the second way in which I can indicate an infinite set. The third is going to be required of almost every problem you work in this particular section. It is called interval notation. And it is using one of the following to indicate this particular set of numbers. You will either have two brackets, a bracket and a parentheses and a bracket, or two parentheses. That's the only four possible combinations of brackets and parentheses. Either two brackets, two parentheses, or one of each in the opposite arrangement. All right, I want to use one of these guys to describe this right here. Forget about this part of the graph. This is the part I'm interested in. Notice the right side starts with parentheses. So my right side of my interval notation is going to have a parentheses, and it's a parentheses at 3, and it goes all the way to, some of you know, it goes infinitely to the left, and we're going to indicate that as negative infinity, since it is infinitely in the negative direction. Some books just use infinity for both directions. Hawks uses a negative infinity symbol for moving infinitely in the negative direction. Now here's a good thing to keep in mind. I will always use parentheses with an infinity symbol. So if I have an infinity symbol on an interval notation, it will always have parentheses. Why? Because bracket indicates you get to or include a number. Infinity is not a number, and I never arrive at something called negative infinity. You know, add one more and it's negative infinity and 1. It's not like that. This indicates an infinite movement to the left, and since I never arrive at a particular value, I will always use parentheses with my infinity symbol. All right. Well, let's practice one of these guys. Let's do, a little bit different. Let me give you a statement of inequality. And it's going to look like this. You could read this, -4 is less than x is less than or equal to 7. And when you do read it that way, if you're like me, you find it very unenlightening. That is not very helpful. I'm trying to figure out what x is. -4 is less than x is less than or equal to 7. That doesn't help. A better way to read this is x is in between -4 and 7. Oh, look at that. And including 7. See that equal to symbol? Oh, that means also include 7. No equal to symbol here, so -4 is not included. A good way to think of this expression is all the numbers between -4 and 7. Oh yeah, and including 7. So if I were to make a number line out of this guy, I'm thinking important values would be -4 and 7. And you guys know that negative numbers are to the left of positive numbers. So here are my two values, -4 and 7. X is anything in between that, so I'm going to just indicate anything in between that for my graph. And now I got to put some ending markers. Remember, if the value is not included, it gets parentheses. If the value is included, it gets brackets. Aha! So there's the distinction. And here's a good thing to remember. If I have just greater than or less than, I'm going to be using parentheses. If I have greater than or equal to, less than or equal to, I'm going to be using brackets. Since there is a less than or equal to between related to the 7, I'm going to use a bracket at the 7. No equal to here, just parentheses. So there's my number line. Now the number line, once you got the number line, you are well on your way to getting the interval notation. Remember, the interval notation is just the Cliff Notes shorthand version of what you see on the number line. Hey, it starts with a parentheses at -4 all the way to 7, and 7 is included with brackets. Notice this, all the important stuff, all the grain, none of the chaff. Parentheses, brackets, from -4 to 7. All right. So these three ways to indicate infinite sets are going to be very important as we answer the questions on our Hawks problems. All right, our next concept is going to be inequalities involving fractions. Kind of like adding insult to injury, huh? Inequalities and fractions, oh great. But we're going to find out that they work basically just the same as with equations. The same steps apply. Let's see if we remember when we look at this guy. And for the record, this guy is this expression right here, the same thing we used right here, is called a double inequality. This is a double inequality. Why is it double inequality? Yeah, well, it's kind of obvious, right? It has two inequality statements. Here's the first statement. 14/8 is less than the fraction. Here's the second statement. The fraction is less than 18/8. Put them together, since they're both talking about this fraction in a double inequality. All right, we want to solve this guy. And in wanting to solve it, we want exactly the same result as we did when we solved equations. We want to get x by itself. All right, first thing I notice is I got fractions. Oh yeah, I think I remember my steps in solving an equation with fractions. It's the same steps in solving an inequality. My first step is to find the LCM of all my denominators. Find the least common multiple of my denominators. Remember what that means? It means the smallest, least, the smallest number that each of these will divide evenly into. Well, what's the smallest number that 4 and 8 will divide into? That's got to be 8. Once again, as you look at multiples of 4, 4, 8, 12, 16, etc. Look at multiples of 8, 8, 16, 24, etc. I notice that the smallest, the least value that is common to both my lists is 8. So find my least common multiple. Got it. It's 8. You remember the next step? Multiply every part by the least common multiple. Hey, same thing as with the equation. Multiply every term or part by, in this case, 8. And since I have fractions, I'm going to put 8 over 1. Remember my strategy here. Remember why I'm doing this. I'm doing this to get rid of my denominators. Again, don't multiply the tops. That's not the point. Let your denominators cancel. 8 will go into 8 one time. 4 will go into 8 two times. 8 will go into 8 one time. 1 times 14. Hey, this no more fractions. 2 times x plus 6. I could do that in my head. Actually, I could do that in your head, but then I might discover something there I do not enjoy. So I will just leave it undone right now. 1 times 18. So let's go ahead and simplify this. Remember, our ultimate goal is to get the x by itself. I want the x by itself, which means I want the part that involves the x by itself first. So I'm going to get rid of 12, do the opposite, minus 12. Again, divide by 2, and I'm there. 1 is less than x is less than 3. Another way to think of it is x is in between 1 and 3. This is my statement of inequality. I could use the very highfalutin set builder notation, the set of all x such that x is a real number and x is in between 1 and 3. I could do that, but this is good enough. My number line, I think I better have 1 and 3 on my number line. And I'm talking about x is anything in between those. So here are all my x's. Here's all the possible solutions, an infinite number of solutions right there. Hey, no brackets. I'm sorry, no equal signs, so no brackets. No equal signs, that means parentheses. This is my number line. And if I wanted to use the interval notation, it's just going to be all the good stuff. Parentheses at 1, all the way to 3. Parentheses. Parentheses at 1, all the way to 3. More parentheses. Hey, if I got parentheses on both ends, I'm going to have parentheses on both ends for my interval notation. That's it for inequalities involving fractions. Same 2 steps as I use to solve equations involving fractions. Good news there. All right. Let's look at inequalities involving absolute value. Now, notice 2 different possibilities here. There are 2 possible scenarios, and they are solved differently. First of all is something like absolute value is less than a number. The other scenario, obviously, is absolute value is greater than a number. They are going to solve differently. So let's focus on this one first. Let's do a example. There's an absolute value is less than, I'll go ahead and make it less than or equal to, it's just the same, 11. Absolute value of 2x minus 1 is less than or equal to 11. All right, the thing to remember about absolute value is less than a number is that it translates into a double inequality. Hey, we just talked about double inequality, right? This is going to translate into a double inequality. And the thing that's in the absolute value goes in the middle. Please notice, there's no more absolute value. It translates into a double inequality without absolute value. So there's no absolute value when I translate it to the double inequality. I keep the same symbols. And on either side, I put this number and its opposite. That's not so bad, huh? So the number goes right there. Its opposite goes right there. So 2x minus 1 goes in the middle. Whatever's in the absolute value goes in the middle. And it is in between the number and its opposite. Hey, that's just like what we just solved. All I need to do is get x by itself. I think I'll add 1 to both sides. Or I should say, all 3 sides. Divide by 2. And I discover that x is anything in between -5 and 6. If I wanted to do that on a number line, x is anything in between -5 and 6, making sure I put my smaller value on the left. Hey, check this out. Got me some equal to signs here. Means I'm going to have brackets. So here's a really good true-false question. 6 is an element of this particular solution set. Is 6 an element here, part of the solution set? Yes, it is. This bracket says 6 is part of the club. -5 is part of the club. Because why? They got the brackets to indicate their membership. All right, interval notation, all the good stuff. Bracket at -5, all the way to 6, bracket again. And Hawks will ask you to indicate your solution set with interval notation. So this is what they're expecting to see. All right, that's how absolute value is less than a number works. It translates into a double inequality. All right, how about the other possibility? Absolute value is greater than a number. This guy translates into 2 inequalities, or 2 inequality statements. In an or relationship. In other words, it's going to be this or that. It is a this or that statement. Let's use the same values except reversing my inequality. We want an absolute value is greater than a number. Here's the absolute value. Let's make it greater than, we'll go ahead and make it greater than or equal to 11. See the difference? Absolute value is less than, absolute value is greater than. All right, this is going to translate into 2 inequality statements. The first one is easy. Just drop the absolute value markers and you got the first statement. That's all I did. Just drop the absolute value markers and you got it. This, or my second statement, again, I drop the absolute values, reverse my inequality symbol, and take the opposite of my number. So this is the opposite, and this is reversed. Hey, it looks just like this, except I reversed the inequality symbol and I took the opposite of my original number. So all I need to do is solve both of those inequality statements. Again, how do I solve an inequality statement? Get x by itself. Get x by itself. So let's add 1 to start with. 2x is greater than or equal to 12, or x is less than or equal to negative 10. Divide by 2, x is greater than or equal to 6, or dividing by 2, x is less than or equal to negative 5. All right, that's the statement of inequality right there. That's the statement of inequality. Let's do the number line. Sorry, I got some sunshine going here. My key values are negative 5 and positive 6. So here we go. All right, on the same number line, just one number line, I want to graph everything, every x that's greater than or equal to 6. So greater than 6 would be in this direction. Oh, wait a minute. It's greater than or equal to. It has an equal to symbol, so I have to have brackets here. So there's everything greater than or equal to 6. Secondly, I want to graph all the x's that are less than or equal to a negative 5. Less than negative 5 is in that direction. Less than or equal to negative 5 means I include negative 5 in my graph. So here's my solution set. It's everything from negative 5 that way. It's everything from 6 that way. That's the solution set. Everything like that works. Hey, if you want to find out if you did it right, pick a value that's in the part that doesn't work. Say 0. 0's in there, right? So let's see if 0 gives me a true statement. It shouldn't, because it's not in the solution set. 2x minus 1 greater than or equal to 11. Let's see if 0 gives me a false statement in this original inequality. 2 times 0 is 0, minus 1 greater than or equal to 11. 0 minus 1 is negative 1, greater than or equal to 11. Absolute value negative 1. 1 is greater than or equal to, no, that doesn't work. And it shouldn't work, because 0 is not in the solution set. Go ahead and try some numbers. Greater than 6, like 7, 15. Less than negative 5, like negative 10. And see if they give you a true statement. You will discover that they, in fact, do. All right. Now I need to indicate the interval notation. This is my number line. I need to indicate the interval notation. It's going to be in 2 parts, obviously, right? Here's the first part. Just do them separately. So from negative infinity all the way to negative 5, and remember I always use parentheses with infinity symbols. So from negative infinity to all the way to -5. What do I have at -5? Got me a bracket. Together with, and the way we write together with when we're talking about sets is like that. The union of two things. It means this is the symbol for or. And it basically means together with. Both of these are part of the solution, this or that. Second part of my solution set starts with a bracket at 6. Infinitely to the right, we say all the way to infinity, and I always use parentheses with my infinity symbols. So there's my inequalities involving absolute values. They work differently. Where did it go? Inequalities involving absolute value. The absolute value is less than a number, translates to a double inequality. Absolute value is greater than a number, translates to two inequality statements in an OR relationship. So when you're working absolute value inequalities, the first thing you want to notice is this an absolute value is less than or an absolute value is greater than? And work according to the directions here. All right. We just graphed an OR statement and an AND statement, didn't we? So let's practice this again. Some OR statements. We haven't done AND yet, but let's practice again an OR statement. Something like this. This one does not involve an absolute value. It's just an OR statement. So I got two things to do. First of all, I got to take care of this guy right here. Little distributive. -5 times -1 is +5. Hey, this is going to be pretty easy. All I got to do is subtract 17. And I got z is less than 5. All right, got to get rid of this 5 here. -5z is less than or equal to 40. All right. You might have recalled at the very beginning I said solving inequalities works almost exactly the same as solving equations, with one exception. Here it is. And most of you are familiar with this. To get z by itself, I need to divide both sides by -5. And here's the exception. When I divide both sides of an inequality by a negative number, or when I multiply both sides of an inequality by a negative number, you know what happens, right? The inequality symbol switches. It flips. So this is negative over negative, still positive z. The inequality symbol switches. 40 over -5, -8. So z is anything greater than or equal to -8, and z is anything less than 5. All right, let's graph the OR solution. Here's my ultimate solution in inequality statements. Let's graph this guy. Little upward pointing number line there. That's all right. So my important values are -8 and 5. All right, let's look at this little hint here. Graph both solution sets on the same number line. Wherever there is any mark, that is part of your or solution set. So let's graph this one first. Z is anything greater than or equal to negative 8. So it's anything greater than or equal to negative 8. So all this stuff is good. This is all part of the set. The second part of my statement is Z is less than 5. So I'm going to indicate anything less than 5. Oh my goodness, look what happens. When I indicate everything greater than negative 8 and everything less than 5, there's not a place on the number line that is not touched by a mark. Everything is covered. That means my solution set is all real numbers. Everything works. The way I indicate that with an interval notation to indicate all real numbers is from negative infinity, parentheses, remember, all the way to positive infinity. That's my solution set. And you will have at least one of these like this that has all numbers as a solution set on your Hawks. So keep that in mind. It's a very real possibility. All right, let's do an AND statement. Make one kind of similar to the last one. Notice the difference. Or, and. Okay, let's solve these guys for t. Negative 2, negative 1 is plus 2. Get rid of the 2. Looks like we're going to have that same scenario, huh? Going to have to divide by negative. Divide both sides by negative 2. What happens? Oh yeah, the inequality symbol switches. Here's my first statement. And get the t by itself, so subtract 11. This is negative t. Negative t. I got to divide both sides by what? A negative 1. Negative over negative is a positive. Dividing by negative, both sides, the inequality symbol switches. 3 over negative 1, negative 3. All right, let's try to figure out what to do here. Here's my hint. And by the way, when you do your quizzes, when you do your test, have this stuff there so that you can look at these hints, look at the examples, and you'll be hopefully well on your way to being able to handle this. All right, number line. My important values are negative 7 and negative 3. All right, graph both sets on the same number line, just like before, with different colors if possible. Your solution set is wherever the two graphs overlap. So let's see. My first set is anything greater than or equal to a negative 7. That means I'm going to include negative 7. And is anything greater than that. So I'm going to indicate with the black here, anything greater than or equal to negative 7. My second set is anything greater than negative 3. So I'm going to graph this with a different color. No equal sign, so I got a parentheses, and it's greater than, likewise still this way, greater than negative 3. Now check this out. Your solution set is wherever the two graphs overlap. That's why it might be nice to have two different colors when you're doing this. Do one of them in yellow, one of them in blue, and whatever's green, that's your solution set. So wherever the two colors overlap, that is my solution set. So it's obviously everything to the right of -3. Now here's the important question. Is -3 in both sets? Obviously it's in this set right here, the black one. But is it in the pink set? There's something marked here, but is -3 part of this set? No, it is not. The parentheses means -3 is not part of this set, therefore it can't be part of both sets. The overlap is the set of all points that are in both sets. That's why we overlap. So my solution set is this. Doesn't include -3, it's everything to the right. There's my combined solution set right there. Once I indicate both graphs and see where they overlap, that's where they overlap right there. That's the number line. The interval notation is parentheses at -3 all the way to infinity. Always parentheses with infinity. All right. So OR statements, wherever there's any mark on your graph. AND statements, wherever the two graphs overlap, keyword. All right. One final little observation here. You're going to want to keep this little sheet handy. It's going to come in handy multiple times. Exceptions involving absolute value. There are exceptions involving absolute values in equations, absolute values in less than statements, and absolute values in greater than statements. Let me give you an example. Absolute value. Absolute value equals a negative number. Now, I don't know if you remember this from last time we were looking at equations that involve absolute value. Here's a question I would ask of you. How often is the absolute value of something equal to a negative number? How often does this happen? Answer, this never happens. Why? Absolute value is always positive, right? Absolute value will never be equal to a negative number. Never happens. And since it never happens, what is my solution set going to be? No solution. Hey, nothing is ever going to, I can't pick an X in here. I don't care if it's -1,000. I don't care what it is, such that when I take the absolute value, it's going to be a negative number. Why? Because absolute value is never equal to a negative number. Got that? When you see an absolute value equated to a negative number, stop. Don't try to work this out. There's nothing to work out. This doesn't happen. Since it never happens, you have no solution. Right, let's use the same two statements. Except this time, let's make it a less than. Now here's the same question I would ask. How often does this happen? How often do you take an absolute value and get something less than a negative number? Now think about this for a second. What kind of numbers are less than negative numbers? Oh yeah, more negative numbers. The only thing less than a negative number, the only thing less than -5 is more negative numbers. How often does this happen? Never. I never take an absolute value and get something less than a negative number, which would mean it would have to be negative. This never happens. Since it never happens, what do you think my solution set's going to be? Absolutely no solution. Absolute values are never less than a negative number. All right, final exception. Notice I'm still using the same two expressions. In this case, greater than. I'm sorry, should be negative. Negative numbers. Absolute value of 2x plus 3 is greater than a negative 5. Again, how often does this happen? When I take an absolute value, how often is that value greater than a negative number? Okay, think about it. Absolute value is always going to be positive. Are positive numbers always greater than a negative number? Yes, always. Whatever this is, positive 2, positive 5,000, positive 1/4, positive pi over 16, it's a positive number. Positive numbers are always greater than negative numbers. This always happens. And since it always happens, what is going to be my solution set, do you think? Solution set, since it always happens, solution set is all real numbers. Anything will work. And think about it. Put 100 in here. 2 times 100 is 200. 200 plus 3, 203. Absolute value of 203 is 203. Is that greater than negative 5? Yep. How about negative 1,000? 2 times negative 1,000. Negative 2,000. Negative 2,000 plus 3. Negative 1,997. What's the absolute value of negative 1,997? It's positive 1,997. Is that greater than negative 5? Yep. It's always going to work. So my solution set is all real numbers. Here's why I give you these exceptions. When you see an absolute value related to a negative number, either by an equation or an inequality, you're not going to have a problem to work out. You're going to have a problem to think out. If it's an equation, never happens, so there's no solution. If it's an absolute value less than a negative number, never happens, no solution. If it's an absolute value greater than a negative number, that always happens. The solution set is all real numbers. So once again, absolute value related to negative numbers, equation or inequality, you're either going to get nothing or everything. All right, that's a lot of information to take in. I will get this onto my YouTube channel, and then I'll put the problems on shortly. Good luck to you.